So in this video, we're going to find the derivative of this vector function in R3, which is 3 dimensions. Now, first of all, what you need to know is that the slope, essentially the slope idea that we get from a derivative, so the slope at a certain point on a space curve is actually going to be a vector. It is a direction vector. It's a vector that is tangent. It's a tangent vector. That's what I wanted to say. It's a tangent vector. So the idea that we think about when we think about slope, we think about derivative, it gives us a vector when we do that. So if we take the derivative of this entire space curve, we will get a new space curve, and that is the derivative of this original space curve. And so at every single point, we're going to have a vector that is essentially the tangent vector, and each of those vectors, if we essentially create our new space curve, will essentially create a new space curve. So it's a very interesting idea. I hope you can visualize this in your head and just know what this is doing before you solve, because this is easy, right? This is not hard to do. So again, r of t is just equal to your vector value function. So it's going to be t minus 2 comma 3 comma t to the negative 2. Remember your vector notation here, and then you just take the derivative. So this is literally what you need to do. You take the derivative of each individual part, and you're done. That's pretty much all you got to do. So each individual component, take the derivative, and you're calling it good. So this, actually, I should rewrite this, is t minus 2 to the 1/2 power. So if I wanted to take the derivative of this, I can take this 1/2 in front, and this is t minus 2, and then raise that to the 1/2 minus 1, which is going to give you negative 1/2 power, or of course, I'll write it out first, negative 1/2 power, or of course, 1 divided by 2 root t minus 2. 1 divided by 2 root t minus 2. That's also an equivalent way. Then you take the derivative of this guy. Oh, and also I forgot to do this, but you should do this. Is basically you have to multiply this by 1, because okay, let me get that back. So you had 1/2, and then t minus 2 raised to the negative 1/2, and then remember, you're doing like the chain rule here, right? You're doing a chain rule here. So what you need to do is you need to multiply by the derivative of the inside, which actually I skipped because it's just 1. But I should show that to you because you might forget it, so it's important. So this is 1 over 2 square root of t minus 2. Very simple, very simple. Okay, so hopefully you got that, and then this is just 0, and then this is t to the negative 2, not t minus 2, so t to the negative 2 is just negative 2 t to the negative 3. Very simple power rule, bring that down, and then subtract by 1. Easy, easy. Negative 2 over t cubed, basically. And that is your new vector function that you get, which is the derivative of the original vector function, right over here. Now, what does this represent? We said this in the beginning of this video, but what this represents is, of course, the new vector function that we obtain, and if we plug in t values here, we'll get a new space curve, a curve in space. This idea, let me go ahead and draw something out so you can visualize it. This idea that we have 3 dimensions, so the z-axis, the x-axis, and the last one always is trouble. That's good. So this is your x-axis, your y-axis, and your z-axis. Some people draw it a little differently. It is completely okay. Your x is basically the one that's going to be pointing at you. So I can't do this because it's a 2-dimensional screen, but it's pointing towards you. So imagine this arrow is pointing towards you. That's what we think about when we think about the x-axis. Now, okay, that's not what we're talking about here. What we're talking about here is what this vector function represents. I'm not going to graph it because you can't just graph it by plugging in points. That would not be completely the thing that you want to do. You should actually, there's different ways to do that, but that's not this video. We're basically, what we're doing is we plug in values for t. So plugging different values for t, we don't have a t here, but if we plug in different values for t, we essentially obtain a vector. We obtain different vectors for different values of t. And so all of these vectors, they're going to point at different points. So different values of t will point at different points. Now, there's many values of t, infinitely many values. And so if you get all of these points, right, there's a bunch of points, all these vectors are pointing to different points. And, you have some longer ones, you have some shorter ones, and all of these, they create this interesting looking space curve, this curve that goes through space like that. This is not the space curve that this represents. This is vector function represents. But yeah, this is just how the idea is. I hope you can see this now. It's a very interesting idea. So that would just keep on happening, and you'd get your space curve however it looks in space, in 3D, R3. And this is not just in 3D. You can also think about a vector function in 2D. It's a very similar idea. You have, let me do that in white. You have your two axes. This is your x and your y. You've seen that before. You can even literally, this connects to the idea of a parametric representation, except you're writing it as a vector function, right? It's just a fancy way. For example, let's take an example, and I know it's taking this video unnecessarily long because this is just for one example, but if we had y equals to x squared and wanted to rewrite this as a parametrically defined function, or a curve, I should say, what I could do is I could use trivial parameterization, which is probably the best way here. I could do x of t is equal to just t, and then y of t is equal to t squared. So plugging in x into here would just be x squared. So that's what you want to do. Y equals x squared. So I just write this as x is t and y is t squared. Now, if you wanted to write this as a vector function, you could write this as r of t was equal to, and don't confuse it with this r of t, it's a different r of t. So r of t, and typically we use r for our vector function things, for our vector functions, so that's why this is t and t squared, and that's your r of t. So you can actually literally do the same idea we did here in 2D. So plugging in different values for t, and what you do is get different vectors in 2D though. And let me actually draw the shape here because I know how it looks. It's gonna look something like that. So if we okay, let me do the real points. Why not? If we do 0, we get 0, 0. So that would be just like a vector with the magnitude of 0. And then if we do 1, we'd get 1, 1. So that's 1, 1 here. So this is a vector that's going to point to this location. Hope you see that. And then if we do -1, it's -1, 1. So it's here. And then you would have a vector that points to that point. And then so that would get you the points, and you can connect the points and then build your vector, so or your function. And so you could do it with a two-dimensional R2 function. Okay, so it doesn't have to be just for space curves. It's a very simple idea. I just hope that you can see that it's a very simple idea, and I hope you can see that it connects back to R2. And so just a side note there. Okay, but yeah, the video was supposed to be for this problem, and that is the solution, and you are done.